Hey folks, today we're going to be looking at disjoint sets. This is a new ADT, and so we're going to look at a few different implementations as well as analyze those implementations to see which is best and under what circumstances. As you can see, I'm trying something new with a pre-prepared PDF, so hopefully today's video is a little shorter than previous videos. So let's jump right into it. For readings, we're in chapter 21 of the textbook, section 21.1 to 21.3, and a good exercise to try is 21.2-2. Now, the idea with a disjoint set is that we have some finite universe of elements. In this case, the finite universe is this bean shape, and there's some elements in it. And we want to partition it into various disjoint subsets. Here we have 3 subsets, and if we label these, just label a few of the elements, I want to check which objects are in the same set. So I want to see is A and B in the same set, or is A and C in the same set? Are A and C in the same set? So the ADT has a set of objects, a set of partitions, where partitions are disjoint subsets of the set of objects. We want to be able to join up partitions. So suppose we have the picture down here, we might want to join the sets that contain A and the set that contains A to the set that contains D. And so we end up with a picture like this. And we want to decide whether 2 elements are in the same set. So are A and B in the same set? So to motivate this, we can look at various applications. If we have a computer network, we might want to ask, are 2 computers on the same network? So maybe the U of T network is comprised of a series of computers, and I can add a new computer to this network. But suppose York has its own network. We might want to ask, is this computer and this computer connected in some way, i.e. are they on the same network? We can do the same with Wikipedia pages or any web page. Are all pages on Wikipedia connected in some way? Well, the answer is no, but you might want to ask, are any 2 particular Wikipedia pages connected via hyperlinks, or any 2 web pages, are they connected in some way via hyperlinks? In which case, this picture changes to web pages, and the connections between them are hyperlinks. And we can make it directed or undirected. And instead of modeling this with a graph, we'll model it with this ADT, the disjoint set ADT, because if it's reachable, then we say it's in the same set. And a slightly more practical way, we could look at components within a computer and ask, are 2 particular transistors on a silicon chip, on a CPU, are they connected in some way? Or are they completely disparate and not able to affect each other? That's a question an electrical engineer might ask themselves when designing a chip or programming an FPGA. In a physical system, we might have a situation in 2 dimensions, but you can easily extend it to 3 dimensions. We can look at a grid of boxes. And of course, this grid could be 3-dimensional. And we might, want to model water falling through this grid, so water falling through a tube, and we say two parts of the grid are connected if water can flow through there. So maybe there's something blocking the tube, in which case we say, oh, these two grid points are connected, these two grid points are connected, these two grid points are connected, and so on. And then we want to ask the question, can water flow from the top to the bottom? It's the same as asking, well, let's add this point and say it's connected to every portion of the top of the grid, and this point, and we say it's connected to every portion of the bottom of the grid. And then we ask this one, called it A, and this one, call it B, are A and B in the same set? Well, they're only in the same set if there's some sequence of pairs of points in the grid that we've already declared to be in the same set, which goes all the way from top to bottom. In the picture I've drawn here, it's not the case. I haven't done many of these union operations, but you could imagine the situation where it is the case. And of course, you extend this to 3 dimensions, and it becomes a way to model flow through a 3-dimensional space. And perhaps there are other applications, and I'll let you think of those applications yourself. For convenience, we're going to label all the points or all the elements of our sets with the numbers 0 to n minus 1, or 1 to n if you prefer. And we don't need to worry about the objects being stored in these sets because that's something that client code would worry about. So just like when we implemented the dictionary ADT, we only worried about inserting, searching, and deleting keys. Here we're only going to worry about the elements 0 through n, and imagine that they're associated with some other object if we're dealing with universes of elements that aren't the numbers 0 through n. As a side note, any finite set is isomorphic with a subset of the natural numbers, and so or a finite subset of the natural numbers at that, and we can make that subset a contiguous subset as well. So this is a nice model for our implementation and explanations. So let's say we start with a set from 0 to 9. So the universe is just 10 elements. And we want to do 4 union operations. Well, in this case, 3 and 9 are going to be in the same set. 8 and 4 are going to be in the same set. 2 and 3 are in the same set, which means 2 has to be over here in this set. And 5 and 6 are in their own set. And so we've looked at 2, 3, 4, 5, 6, not 7. We've looked at 8 and 9, which leaves us with 0, 1, and 7. So 0, 1, and 7 are in sets all by themselves. And now we can ask, are 2 and 9 in the same set? Well, in the picture we have here, we can see very clearly that 2 and 9 are in the same set. But that's the type of query you might want to do. Our goal here is to design an efficient data structure to perform union find. If we look above, we performed union operations, and we performed a find operation. And a few things we want to keep in mind is that we might perform a series of adding elements, and then unions, and then add some more elements, and then perhaps find, and then maybe some more unions. We could do these operations in any order. It doesn't always consist of add elements, then unions, then finds. We could sometimes intermix this order. We could do add element, union, add element, find, union, and so on. The other things we need to worry about are the fact that the number of operations could be large and the number of elements could be large. But note that the number of elements has to be less than the number of operations, because one of our operations has to add an element. So we start with 0 elements and we add elements. And so we've defined a nice ADT here to solve a variety of different problems. We have a finite collection of disjoint non-empty sets, S1 through Sk. If we look at the picture here, we have S1, S2, S3, S4, S5, and S6. Likewise, in the earlier picture, well, right now there are only 2, S1 and S2. And the way we're going to implement or define the find operation is by using a unique identifier called a representative. And you can think of the representative as the name of a set. Since nowhere do we need to store the name S1, we will simply use an element of the set to name that set. So above, we could say S1 is the set that contains 3, S2 is the set that contains 4, S3 is the set that contains 5, and for the rest, they only contain 1 element. And so now, if we want to check if 2 and 9 are in the same set, well, if we look for 9, we get 3. And we look for 2, we also get 3. And so they're in the same set because they have the same representative. So makeSet takes a new element, so one that's not already in one of the partitions of the universe of elements, and we add the singleton containing that element to our collection. FindSet is given an element, we return the representative of that set. So above here, we found 9 and we got 3. And if the set element isn't in the collection anywhere, then we can return nil. For your purposes, or for analysis, we can just assume we always have input. And, or in the worst case, we're not going to assume we have that. We don't need to assume we have valid input, because in the worst case, we're going to have to look everywhere anyways. And for union, we're going to take 2 distinct elements, x and y, that are in the set S, or that are in some Si, which is in S. We're going to look at the set containing X and the set containing Y. We're going to take their union, and let's say we'll call that S union X, Sx union Y. We remove X and Y from S, and then we add S X union Y back to our collection S. And the representative might change. For example, if you look at an example here, we had the union 3, 9. So maybe S1 looked like this. And later, we performed union 2, 3. And let's say the representative before was 9. And then we do the union 2, 3 operation. Well, the new set, S1, is 2, 3, 9. And maybe its representative changed to 3. But it could change to 2. There are no rules about in our ADT that say the representative has to be in a particular element, only that it's in the set. And if they're already in the same set, we do nothing. And of course, we have to assume that x and y are in are each in one of the SIs. A very important application, which we'll see when we get to graphs, is Kruskal's algorithm. You don't need to worry about what Kruskal's algorithm is, or what it does, or even what a graph is. But I've written down the algorithm here so that you can see that first we perform a series of make set operations. So first we add a series of one element sets. And then over and over again, we perform a find set followed by another find set, and then a union operation, possibly. And so we're performing n make sets, followed by n times, and here we'll have two find sets followed by an optional union. So in total, it'll look like find set, union, find set, and then maybe we don't perform a union this time, so we perform two more find sets. So this is just one possible sequence of operations. In this case, the number of operations is equal to n plus 3n in this case, because here there are three operations, and doing that little n times. But we need to keep in mind every possible sequence. This is just one possible sequence that you know will occur in a particular in a particular algorithm that uses the disjoint set ADT. Okay. And the question becomes, how do we implement it efficiently? We're going to stop here and give you an opportunity to think of different ways to implement it. That's in the textbook. And if you have some ideas for implementation, bring them to class and we'll discuss them. Their merits, their pros, their cons, when we might want to use that implementation. And we'll look at some of the implementations that I have here in my notes. And we'll see the canonical implementation, which is fairly standard for this data structure. And we'll learn about a odd little function called the log star function, which we'll use for analyzing this. All right, see you on Tuesday.